Okay, hello everyone. Welcome to the first training in our PLC course. And today's training is about the PID instructions. Sorry, there's some questions about here. Today's training is divided to two parts. The first part, I will introduce the PID control and how does the relevant parameters means and how it works. And for the second part, I will introduce the PID instruction in our PLC. I will show you in the PID function the same for the is the same to LX3V and LX5V. And for the LX6V, the PID function is in a beta version is supported. So this is the PID function system diagram. The PID function is commonly used control method that address the error of the system by proportional, integral, and the derivative control actions to achieve a stability and precision and rapidly. As you can see in this picture, the PID output to the process, and from the process, you feedback the value, and then we compare it to the set point and continue to adjust our PID output. You can use this PID function in very many applications, such as the heating systems. We can use a PID controller to control the gas flow. And when there is a graph, the RTD feedbacks the real-time temperatures and feedback to the PID controller. After compare the set point, and he will adjust the PID output to control the flow rate for the gas. And this is another applications about pressure control systems. The pressure transmitters feedback the real-time pressure signals to our PLC. And when PLC execute the PID instructions, it will output and to control the speed command of the VFD. So we can make the real-time pressure is equal to the set temperature, the set pressure. Okay, because there are three important parameters proportional, integral, and derivative. So let's introduce one by one. The first parameter is proportional. It's controlled adjust to control output based on the magnitude of the error. As we can see it here, this is three different value for the proportional. And this different proportional cause the different control curve here. As we can see, when the value is only 1, the control curve is stable, but it have a large range error here. And when the KP is 5, it still has some error here. It doesn't meet to our requirement target value. And if we increase the KP value, it will also lead the overshot of the curve. Sometimes the overshot is not allowed in our control systems. But with the different range, with the different value of the KP, we can see with the KP increased, the response is more faster. So the KP always used to execute the control speed and shorten some steady state error here. And then this is the second parameters integral. Integral control adjusts the control output based on the accumulative error over time. Because the proportional control doesn't totally eliminate the system error. So we can use this parameter integral to eliminate the error. As you can see here, if the Ki value is only 0.5, the red control curve is match the target value we set, but it also cause the overshot if the value is too high. So to eliminate the overshot, we use the third parameters derivative. Derivative control adjusts the control output based on the rate of the charge of error. It can suppress systems oscillations and improve system response speed, but may increase sensitivity to the noise. Because if we set the derivative too high, it will respond more sensitive to the system noise feedback. We can look at this graph picture. It shows how these three parameters work together to make the control curve more smoothly and more matched to our requirements. At first, only increased the value of Kp, and it still have some state error. Then we increase the Ki value. The state error is eliminated, but the overshot is more. So then we use Kd derivative to decrease the overshot. Okay, this is all to the PID instructions. Do you have any questions about this part? No? Okay, let's continue to the PID instructions in our PLCs. For our LX3V and 5V PLC, the PID instructions have 4 parameters. The first parameters is for storing the target value, such as the pressure or temperature value. And the second parameters is for storing the measured value. Actually, it's the feedback signal, such as we can use the temperature module and move the current temperature to the second parameters here. And for the third is for storing the PID control parameters. And for the last parameters is for storing the output value. We can use this value with the PID PWM instructions to control some controller, something like SSR. And this is the parameters list for the parameter 3, the third parameter here. For example, if the third parameter is D200, so here the value of 200 is for the sampling times, and its unit is milliseconds. For the second address here, it will be D201. It identified action directions and whether we execute the auto turning. For example, here, if we use it as the heating condition, so the positive actions, the bit 0 will be 0. If we use the PID for the cooling control, so the action directions is reverse actions. So you will change the value of bit 0 here. So it means 0 or 1. And then we need to decide whether we use auto turning. It's for bit 4. If we use bit auto turning, so the decimal value will be 16. And if we use auto turning and for the cooling control. So we need to set the value of D201 as 17. If we not use auto turning and we want to use it as the heating control, so we just set the value of D201 as 0. Okay. Any questions about this action direction parameters? Because it is a very important parameters. Okay, let's move to the fourth to the sixth parameters is the PID gain I just mentioned. And for the 8 and 9 parameters is to set the range of the PID output. Usually we set output lower limit as 0 and the output upper limit as 2000. And then there is rest 2 parameters. It's about the maximum ascent rate and the filtering. The maximum ascent parameters, it limits the changing rate of the control output signals to prevent the system from corresponding too quick and cause the oscillations or instability. Yes, if we set as third parameters, for example, for this example, D200. So if we set D201, if we set it as 16, it means we use auto turning and for the heating system, control system. If it's 17, it means we use auto turning and for the cooling system. So we can set the maximum ascent rate to prevent the system from the over adjusting. Because sometimes we use it with the system, the load with a significant inertia. And the last parameters lift filter parameters used to smooth the input signals and reduce the impact of the noise on the systems to ensure that the PID controller receives a cleaner and smoother feedback signals. This 2 parameter is not necessary, but if you can set it based on your requirements. Okay, this is the example program. Just notice that the unit of the first and the second parameter should be the same. It should always be the same dimension. We cannot set, for example, D9 is the degree Celsius, and the unit of D10 is not degree Celsius. And after we triggered X10, we get the output value from D130. Okay, this is the video about the PID control. How does it works? This is for the is record in the offline simulation. So we set the sampling times as 0.5 seconds and using auto turning and for positive action here. And set the range, output range from 0 to 200. Let's check it again. So at first we set the target value is 100. And the feedback value is 0. So because it used the auto turning, so at first the output is the 2000. It's reached the upper limit. And then we increase the value of feedback when it is larger than the target value. The output now is become 0. And then we continue to decrease the value, feedback value. And the output will changed by the system error. Let's see this video. This is the heating systems using auto turning. So here I use the temperature module and get the current temperature is 15.4 degrees Celsius. And as you can see here, I set the target temperature is 30 Celsius degrees. And then we can continue triggered M1 PID control. With the temperature increased, the value changed. When the current temperature is higher than the target temperature, the output will become 0 immediately. So this is not a real heating system. I only put the temperature sensor into the hot water. So the temperature changed very rapidly. And then I put the sensor out of the water. As you can see now, the temperature is decreased. So the output value also changed. And this strip value is the Kp, Ki, Kd. So if you don't want to use the auto turning, you can use these three parameters to set it in the corresponding address. And then it will also have the PID control. As you can see here, the third parameters address is the 1500 here. So the KP address is the 100 and 1503 and 1504 for KI. The 1505 is address for KD. We set the same parameters, and now we set the 1501 as 0, not use auto turning. As you can see, when we trigger M11 here, the output value is not reach the upper limit. It's just about 600. With the current value, the real-time temperature increased. The output value also changed. And when the current value is higher than the target temperature, as you can see the trend, the output value is decreased. So here I can change the target value here. As you can see, once the error is increased, the output value also changed. It's more easier to see here. Now the target value is 300 and the output is very low. But once we set it as 500, the output increased because the system error is increased. And this is the example for the cooling systems using auto control or the auto turning. As you can see here, once we triggered the PID instructions, this value is changed. It's normal. And then, as we can see here, the current value is higher than the target value but the output value is reached to the upper limit because now it works as a cooling system. With the temperature become more lower, we can see how the output value changes. Now the current value is smaller than the target value. The output now is 0. And when the current temperature is higher than target, the output back to the higher limit again. Please notice that because this example, I use the temperature sensor directly to put it in the hot water and out of hot water, the output value is not very relevant to the current value changes. So as you can see, the output it doesn't very smoothly changed with the current value. But if you use this command in the real application, it will be more reliable here. As you can see now, the current value is smaller than the target value again. The output in a very low level here. Okay, this is all to the demonstration of the PID instructions. Do you have any questions? Okay, this is all to today's training. Thanks for attend today's training, and the next training will be in the Tuesday next month. It's about the Econ function. CCPID doesn't mention in today's class. You can refer it in our Wecon support center. You also have the introduction manual. Yes, all this manual is documents is about. You can get it in our Wecon support center. Today's presentation, I will share it in our group. And also for the demo showed in the video. And today's training also have the after class exercise is about to use the PID control instruction to make a cooling control and doesn't use the auto turning. I will provide the value of KP, KI, KD we should set here. And please do remember the whole training is for 6 lesson class, but if you don't submit the after class exercise for more than 2 times, you are not allowed to attend the final exam. So please arrange your time to submit all the after classes exercise. Yes. Thank you to you all. Goodbye, everyone.